Slope angle 22 degrees. Vehicle weight 41 tons. Road width 3 meters 70 centimeters. Required turning radius 11 meters. Available space 7 meters. The M26 Pershing turned left. The track slid. The right side lifted. For 1 second, 41 tons of steel balanced on the edge of physics. The tank did not malfunction. The engine was running. The math was correct. But the world was not the world the math had assumed. Lieutenant crews inside the Pershing felt the shift before they understood it. Metal groaned. Gravel collapsed under the right track. The center of gravity moved sideways. Not much. Just enough. Enough to kill everyone inside. The turn was not completed. And in that unfinished turn was an engineering lesson no classroom had prepared them for. The M26 Pershing was one of the most advanced heavy tanks of its era. Designed in the final phase of World War II, it weighed 41 tons 900 kilograms. It carried a 90mm main gun. Front armor thickness reached 112 mm. The Ford GAF engine delivered 550 horsepower. Maximum road speed reached 35 km per hour. On paper, it was a balanced machine. Its track width was 61 centimeters. Ground pressure averaged approximately 85 kilopascals. Turning was achieved through differential track control, one track slowed, the other accelerated. On flat, solid terrain, the tank could pivot with a radius of roughly 4 meters when one track stopped completely. In Europe, this worked. In Korea, it did not. 75% of the Korean peninsula is mountainous terrain. Roads in 1950 were narrow remnants from Japanese occupation, often 3 to 4 meters wide, covered in gravel, dirt, fractured stone. Slope angles frequently exceeded 20 degrees. Hairpin turns were tight and unforgiving. The Pershing had never been designed for that geometry. Turning a tank is not simply a mechanical action. It is a physics problem. When a vehicle turns, centrifugal force acts outward from the curve. The magnitude of that force increases with the square of speed and decreases with turning radius. On a slope, gravity already pulls the vehicle downhill. Combine centrifugal acceleration with lateral gravitational force, and the effective center of gravity shifts. The M26's center of gravity sat approximately 1 meter 20 centimeters above the ground, centered between the tracks. Under static conditions, the tank could tolerate lateral slopes approaching 35 degrees without tipping. But static conditions are fiction in motion. When turning on a slope, the center of gravity shifts dynamically. The support base of the tank is defined by the area between its two tracks. If the projected center of gravity moves outside that base, rollover begins. And rollover does not announce itself in advance. It happens suddenly. On flat European roads with high friction coefficients, approximately 0.7 to 0.8, the tracks gripped the surface reliably. Differential turning worked efficiently. But on Korean gravel and loose rock, friction coefficients dropped to between 0.3 and 0.5. Sometimes lower. Low friction created two problems. First, sliding replaced controlled turning. Second, when one track stopped and the other advanced, the tank did not pivot. It drifted. Drifting on a 3-meter wide mountain road is not a maneuver. It is a countdown. Reports began arriving from the field. Tanks unable to complete tight turns. Vehicles sliding toward cliff edges. Crews forced to reverse repeatedly in multipoint maneuvers. Some tanks rolled down slopes. Not because of enemy fire, but because geometry defeated horsepower. The Pershing was not failing mechanically. The engine ran. The transmission worked. The gun fired. The tracks held. The failure was environmental mismatch. The tank had been optimized for the European theater, wide roads, moderate slopes, stable ground. Engineers had assumed those parameters. All calculations, center of gravity height, track width, turning radius, load distribution, were based on that environment. Korea was outside those assumptions. Mathematically, the situation could have been predicted. Center of gravity position was known. Road width was measurable. Friction coefficients could have been estimated. Dynamic rollover thresholds could have been calculated. But those calculations were never made, because the operational model assumed Europe. In the field, adaptation became necessary. Crews learned to reduce turning speed to nearly zero. One track was stopped fully, the other advanced slowly, minimizing centrifugal force. Infantry units were ordered to widen roads before tank passage. Rocks were removed by hand. Slopes were measured visually before committing to a turn. This was not armored warfare. This was emergency civil engineering under combat pressure. Post-war analysis identified the core issue: environmental assumption error. Not insufficient horsepower. Not flawed armor. Not inadequate firepower. A world model mistake. The bridge engineers had once misjudged dynamic redundancy. The Pershing designers misjudged terrain geometry. In both cases, the mathematics was internally correct, but the boundary conditions were incomplete. Engineering does not produce universal truths. It produces conditional truths. If environment equals X, system performs as Y. Change X. Y changes. After Korea, tank design philosophy evolved. Center of gravity was lowered in subsequent models. Turning radii were reduced. Track systems were refined for better performance on unstable surfaces. Most importantly, multi-environment testing became standard procedure. Tanks were evaluated not only on plains, but in mountains, deserts, swamps. Assumptions expanded. The M26 Pershing was not a bad tank. It was a tank designed for a different world. Perfection in engineering is contextual. Remove the context, and perfection dissolves. Every system carries invisible assumptions about terrain, temperature, load, friction. These assumptions rarely appear explicitly in blueprints. Yet they govern every tolerance value, every dimension, every calculated force. When those assumptions are wrong, even flawless mathematics cannot save the result. In the mountains of Korea, a 41-ton machine nearly rolled because the world was narrower than expected. The tank did not fail. The assumption did. And in engineering, that difference means everything.